Hi everyone, welcome to Best Science Brain YouTube channel. Today we're going to look at how we can assess refraction on rectangular glass block. So this experiment is a very simple experiment that is meant to demonstrate refraction of light and also to demonstrate or prove Snell's law of refraction. So it's a very simple one that you can do at home as a student. You can go and buy the rectangular glass block from a scientific store and optical pins. You need the optical pins or 4 optical pins. You also need the math set or mathematical set for this experiment. It's a very simple one you can demonstrate at home and attain or achieve the same result. So if you are not subscribed to the channel, please, as the video is playing now, move down beneath the video. You see the channel's name, Best Science Brain, and the subscription bell or icon. Tap on it once and get subscribed to the channel. So we're going to look at this experiment, and then we're going to do many experiments on this rectangular glass block to assess many ways or different ways by which questions can be asked from this rectangular glass block. So this first one we're doing, we'll call it model 1. We're going to do model 2, model 3, 4, and even 5 to show different ways by which question can be asked from the same specimen. Please, you have to practice, you have to watch the whole video and then practice. Teachers can use it as practice for their students to understand how to do this and do it accurately. It's a very simple experiment that students should not run away from. So let's go to the question we have here. It says, use the diagram above as a guide to carry the following experiment. I trace the outline A, B, C, D or rectangular glass prism of the drawing on the drawing paper provided. So you can see the outline A, B, C, D. The number II says remove the prism, select a point N on AN such that AN is 1/4 of AB. So you look at the point, you select a point AN which will be 1/4 of AB. So you measure AB and then find 1/4 of it. That becomes our AN. The number 3, or I say, draw the normal LNM. Also draw a line, arrow N, to make an angle alpha, 125 degrees, with AB at N. So you look at the normal LNM. That's a straight line, that means a number. Then you draw an angle alpha, that is a glazing angle alpha, 75 degrees to the normal. Then IV fix 2 pins P1 and P2 on the line arrow N. Replace the prism on its outline. So fix 2 pins P1 and P2 on the incident ray. So we now go to the 5th one. Fix 2 other pins P3 and P4 so that they appear to be in a straight line with the images of P1 and P2 when viewed through the prism through DC. So on the other face of the prism DC, look at the images and fix 2 other pins P3 and P4. Then produce line P3, P4 to meet the line DC at O. Draw a line to join NO. So produce P3, P4 to meet the prism at O and then join N to O and N to O, as you can see in the diagram. Then we now go to VII. Evaluate, V triple I. Measure and record the values of MO and NO. So now measure the line MO and also measure NO. So IS says evaluate phi equal to MO over NO, and then find cos alpha. Then S says repeat the procedure for 4 other values of alpha: 65 degree, 55 degree, 45 degree, and 35 degree. In each case, evaluate phi and cos alpha. So let's really understand what we're about to do. We have the rectangular glass block. We want to trace the outline A, B, C, D, as you're seeing it there. After we are done trace the outline, we'll measure AN. First of all, measure AB. Find the length of AB, and then take the 1/4 of AB. So if AB is 12 cm, 1/4 is 3 cm. If AB is 15 cm, 1/4 is 15 over 4. So we'll take 1/4 of AB, and that will become our AN. At that point, AN, we'll draw a straight line. LN, and that becomes our normal. Then we'll draw an angle of incidence. Look at that line moving from, that is where you have the incident ray to N. So at that point, we'll draw it so that the glazing angle, that the angle alpha be 75 degree. Then after that, we'll now view from DC to find the emergent ray. And using the search pin, we'll have to locate the images on the straight line using P3 and pin P3 and P4. After we join P3 and P4 to meet the place at O, then we'll use the straight line, join point O to N. Then we'll now measure MO and also measure NO, and then evaluate other things. Repeat the experiment with angle 65, angle 55, angle 45, and so on. So let's start now. So to start the video or the experiment, we have to trace the outline of the block. So we'll trace it with a sharp pencil. You trace the outline of the rectangular block. Okay. You can call here A, B, C, and D as we have in the diagram. To be fast on this, you have to still trace under one so that you don't waste time on the experiment. Okay. You can see us doing it. And then that. You can call here A, B, C, and D. Having done that, you also trace the third one. Have that. Okay. That is it. With sharp pencil, A, B, D, and C. When you are done that, you now measure the length AB. Use the cm end of a ruler. This is inches, while this side is centimeter. Find the length of AB. The length of AB is about 10.3 centimeter. So AB is 10.3 centimeter. So I'm going to find 1/4 of AB. 1/4 of AB, dividing 10.3 by 4. So let's do it with calculator. 10.3, 1/4 of it, equals 2.58, approximately 2.6. So I'm going to measure 2.6. So this is 0, 2.5, 2.6. I'll mark it here. At this point is the place you're going to draw the number according to the instruction. Also, you measure out 2.6 here, 0 here, 2.5, 2.6. maintain the same distance all through. 2.5, this is 2.6 here. So having done that, you draw a straight line. That is your normal. You draw the straight line passing through this point. And then that straight line, here is your L, here is your N, and this point is your M. The same thing here. Do the same thing over there. Draw a straight line as your normal. So this point is your L. Here is your M, N, and here is your M. The same thing here. You draw also a straight line, passing that through that point, L, N, and M. Having done that, you get your protractor. You see, the line AB, this the baseline of the protractor must cover the line AB. And then the line, the 90-degree line, will cover LN. So you can see that the baseline being covered, the line AB being covered by the baseline of the protractor, and the LN lying beneath the 90 degrees. So the glazing angle here is 75 degrees. 75 degrees. So you count 75 degrees from this side. 0 end of protractor. 10, 20, 30, 40, 50, 60, 70. Then between 70 and 80, we have 75. Or you can count it this way. Since the angle here is 75 degrees, the angle of incidence should be 15. How do I get 15? 90 minus 75 give us 15. Count it from 90, this is 10, and here is 15, you have it. So the alpha here should be 75 degrees. For the score 1, the alpha is 65 degrees. So we'll see maintain the same status, whereby the baseline of the protractor cover the line AB, and then the 90 degrees line covers LN. Now we're measuring angle 65 degrees. So to make it easy for you, subtract 90 from 65. 90 minus 65 give you 25. So from here, count 25. This is 10, 20, 25. Or you can count from 0 to 65. So alpha here is 65 degrees. Then go to the third one. The same thing. The baseline of the protractor covering the line AB, and then the line of 90 degrees covering the normal. So this one is 55 degrees. 90 minus 55 will give us 45 degrees. Being 45, here is 10, 20, 30, 40, and here will be 45. Or you count it from this side. 10, 20, 30, 40, 45. So, having done that, we now join the incidence ray to the normal. So this is where you marked. They go the first one. You join the incidence ray to the normal. You also join the incidence ray to the normal. You see, you have it. You also join the incidence ray to the normal for this other one. But so to avoid error, let's complete this one before we start doing the third one. So we'll start with the first one. Our optical pin. We place one here, and that will present our P1 on that line, please. Make it straight. Then remember, you have to use a soft board. Either a soft board or use a PVC board. Then when you place the first optical pin, as a precaution for this experiment, please, the second pin will lie at least 4 cm. Look at my ruler. From the first pin. Don't make them to be too close. So you can see this 4 cm. At least 4 cm from the first pin. So you do that. And then make sure that the pins are vertically erect, not bending. So let's see. We'll try to maintain them to be erect. When we are done that, we'll return back, or we'll place back the rectangular glass block, so we can view the image or the images of the pin from the face DC. So we'll now start viewing from the other side, the face DC. You cannot view with your two eyes wide open. You have to view with one eye closed and one eye open until you see the images or the pins on a straight line. So that is why we are seeing it. So when you place the search pin, you're going to block the images of the two pins. So you have to stay in a position whereby the images of the two pins, so you have to adjust your head and your eye to the point that the search pin will block the images of the two pins. And when it blocks the images, it means that they are not in a straight line. We then play the second pin to block the first search pin. So that when you look through the second pin, now this second pin that I place here, you'll not be seeing the first pin, neither will you be seeing the images. That means they are not in a straight line. So having done that, we'll now remove the glass block. So we'll remove the prism, then remove these pins, and then join these points, P3 and P4, with a straight line to hit the prism. So this should be a P3, this should be a P4. Why one of these pins be a P1, P2. Incident rate arrow going down, emergency rate arrow going out. So this point on the prism is our point O. This point O. So having done that, we join point O to N with a straight line. We join O to N with a straight line. So having done that, this is our MO, which we are going to measure. We want to measure the horizontal displacement, NO, and the lateral displacement, NO. So let's measure our MO with the CM end of the ruler. Our MO will give us about 1.2 cm. So MO is 1.2 centimeter. Then we'll now measure our NO. Our NO, that is the lateral displacement of the ray. It gives us around 6.5 or 6.6 cm. So NO is 6.6 centimeter. So we'll move to the second experiment now, where the alpha is 65 degrees. We place our incident pins. The first pin on the incident ray, make sure it's straight. Then you maintain, as we said, maintain a distance of about 4 cm between the first pin and the second pin. That's a precaution in optics. Let them not be too close. Second pin, try to keep them on a straight line by viewing their heads. So having done that, we bring back the rectangular glass block, then to cover the outline. We now trade the image from the face DC, the images of the pin from the face DC. How to trace them and make sure we're seeing it in a straight line. So at this point, the images are in a straight line. One pin is blocking the other. Not only with the first pin block the other, then when you know that in a straight line. Then the second pin you're going to use will block entirely the whole pins. So you can see that. So having done that, remove the block, remove these pins, then join them. To join them, we now have this. So this should be our P3, our P4. This point is our O. Remove these other pins, P1, and then P2. Incident ray, emergent ray. They join O with a straight line to meet the point N. That's okay. Having done that, let's measure MO. MO is 1.8. So our MO is giving us 1.8 cm. Then your NO, the lateral displacement, is 6.7 6.7. So our NO is 6.7 centimeter. So move to the third experiment. So the first one, alpha is 75 degrees, second one, 65 degrees, third one, alpha is 55 degrees. So as we said, keep your protractor in a way that the baseline of the protractor cover the line AB, whereas the line of 90 degrees covers the incident ray. So we have it. When I measure the glazing angle here is 55 degrees. 90 minus 55 is 35. So you can count from here 10, 20, 30. So here at this point is at 35. Or you can count from this point 10, 20, 30, 40, 50, 55. So whether you count from this side, you get 55 degrees, or you subtract from 90 and count from this side. So having done that, I'll draw the incident ray at this point. So have that. That's the incident ray. We now fix our optical pin. The first one here. Okay. And the next one will maintain a distance of at least 4 centimeters from the first one. As a precaution, avoid so much closeness. 4 cm. Then having done that, make sure they're in a straight line. And then when you're done that, return the rectangular block and view the images. As a precaution, you must do this experiment at a place when you have enough light rays. Enough light rays. You don't have enough light rays. It's a dull weather, then you need artificial source of light to help in refraction, because you cannot have refraction in the dull weather. It will be minimal. So let's view the images. So you can see the image. You close one eye and slant adjust your head and your eye, the one that is open, until you get the images on a straight line. So you get the second one. The second pin will cover every other, will block every other pin. So that is it. we are there. So having done that, you remove this too, and then remove the prism. We now join the pins with a straight line to the prism. Arrow here, that should be cleaned. The line should not be double. So I have to make it proper. Avoid double lines, please. So I have this, and then that is it. This is P3. Call this one P for the ray is leaving, is emergent. And then these are P1, P2, the ray is entering, incident. Then the alpha here is 55 degrees. So having done that, this point is O. Then join O to meet N with a straight line. Then when having done that, measure MO. Remember, use the cm end of the meter rule. MO is 2 point, let me get it right, 2.1 approximately. MO is 2.1 cm. And then NO, the lateral displacement. NO is can call it 6.8 cm. So you can see that MO, and look at the readings, MO is increasing, while NO is also increasing slightly. The Y variation in MO 1.2, 1.8, and 2.1. And there's a slight variation in NO 6.6, 6.7, and 6.8. So let's go. So we are in order. Let's go to the remaining two. So we're going to the fourth experiment. You can see the outline already drawn for you. And this point, where you have the pencil, is the point N. That is, remember that this point is 1/4. This is 2.6. 1/4 of the face AB. Depends on the length of your prism, because prisms have different sizes. So this one is, the face AB is around 10 points that we measured, and 1/4 of it is 2.6. You maintain that throughout the experiment. So depending on the length of your prism, then you find 1/4. For this one, we'll have 2.6 here. So at this point, we'll draw a straight line. That's our normal. A straight line passing through from the face AB to the face CD. So we'll still do the same thing for the other one. Here, the angle we're going to measure alpha is 45 degrees for this. For this one, we still have to draw also a normal at that point, 2.6 from the point A. Our under normal. This point is our N. Here, our alpha is going to be 35 degrees for the next experiment. So let's start with the first one. We bring our prism, put it here, our protractor, please. We put it here, and then the base down of the protractor will cover the line AB, and then the 90-degree line will cover the normal. 45 degrees, so 90 minus 45 is 45. So 10, 20, 30, 40. So the middle line here is 45. Or you can see count from here, 40, 45. So having done that, we'll now draw our incident ray to the point N. We'll draw it. So we're going to have, bring a ruler closer. Now have our incident ray. Making angle here is 45 degrees. That is our alpha. Then we'll now place our optical pin. We'll put one here on the line. Then we'll maintain 4 centimeter. Maintain 4 cm before we play the second pin. So second pin is around 4 cm from the first. So it's more like it's not on the line. We have to change the position. So you have to be on the line. That will make them to be on a straight line. So you have to be very careful of what you're doing. So having done that, return the prism, and then make sure that the pins are on a straight line by looking at their heads. Okay, we'll now view the image from the face or the other face, opposite face CD. View the image, the search pin. Close one eye and keep one open. Adjust your head until one of the first pin cover the second one as you view through the glass. So at that point, you now put your search pin. Then the second pin will now cover everything. Okay. Having done that, we'll remove the prism. Remove the pins and join this with a straight line. So, and we'll join. We'll have this. So this point is our O. So this is our P3, P4. Remove the pins here. P1, P2, incident ray direction, emergent ray. Then join N to meet O with a straight line. So you can have a displacement produced. So having done that, we measure this is our M, our MO. For this one, our MO is a large value. Our MO is 4 cm. MO is 4 centimeter. So MO is 4 cm. We now measure our NO also. Our NO is giving us a bigger value here. Around 7.4 cm. We go to the fifth one. So this is the normal already drawn. This is our L, M, and then M. M here, please. So we'll put our protractor. The baseline or the protractor should cover AB. As you can see, the baseline will cover AB, while the normal, the 90, will cover our normal. They make it okay. So it's more that the line is bending, so we'll have to clean it. So now mark our angle 35 degrees now. So 35 degrees, you count from this side 10, 20, 30, 35. Or you subtract 35 from 90, that'll give you 55. And you count from this side 10, 20, 30, 40, 50, and then 55, the same thing. So having done that, you then draw your incident ray here. That is it. So having obtained that, we place our optical pins, maybe our P1 here on that line. Then our P2, maintain a distance of minimum 4 centimeter. Make sure you keep the same distance. If you want to use 5 cm, no problem, but minimum 4 cm, but maintain the same distance all through the experiment. So this is the second pin here, there. So on the line, I have to make sure the pins are on a straight line by looking at the head of the first one. So if you view the head of the first one, you can see that on a straight line. Then you bring your block and then view the images of the pins from the face CD. So look at the images. Let's see. Let me maintain this one on a straight line. On a straight line. For you view the images. You close one eye and keep one open. And slant your head. Slant your head to get the images. Okay. I'll put the second pin to cover the two, cover all of them. So that is it. So we'll have it there. When it's slanting. Let me do it very well. The second pin to cover the first one and every other thing. So we'll have it there. So having done that, we'll remove the glass block, remove the pins, join them with a straight line to meet the prism. Then this is our P1, P2, the incident ray, emergence ray P3, and then P4. So this place is our O. We join O to meet N with a straight line to find the lateral displacement. So have that done. And mind you, here is your M. So let's measure our MO with the CM end of the ruler. Our MO, if you've measured, it's giving us a value of about 4.3 cm. Let me get it right. 4.4 cm. Let me get it right. MO is 4.4 cm. When I measure NO, our NO give us, to get it right, it's giving us around 7.8 cm. So, having done this, we're going to collect our readings. Our readings for the experiment, the angle alpha 45 degree, MO is this 45 degree here, MO is 4 cm, 4.000 to make it to 4 SF. NO is 7.4 cm, 7.400. Look at the heading, MO and NO. Then for angle 35 degrees, our MO is 4.4 cm, 4.400 to make it to 4 centigram figures. Our NO is 7.8 cm, 7.800 centimeter. For 75 degree alpha 75 degree, our MO is 1.2 cm, 1.200 recorded there. Our NO is 6.6 cm, 6.600 to 4 SF. When alpha is 65 degrees, our MO is 1.8 cm, 1.800, and NO is 6.7, 6.700 to 4 SF for consistency. When alpha is 85 degrees, and MO is 2.1 cm, 2.100, and NO is 6.8 cm, 6.800. So you take a look at our readings. The value of MO is increasing 1.2. At the angle decreases, the value of MO increases 1.2, 1.8, 2.1, 4.0, 4.4. Likewise, the value of NO also increases as the angle decreases 6.6, 6.7, 6.8, 7.4, and then 7.8. So we're going to find now 5, that is MO over NO. We're going to divide MO by NO for each experiment. We're going to divide MO by NO for each experiment. So the first one, we're going to look at phi, which is MO over NO. Phi has no unit because CM cancels CM. For the first one, divide 1.2 by 6.6. For this one, we'll divide 1.2 by 6.6, we get 0.1818. For the second column, second row, divide to find the ratio M over NO, divide 1.8 by 6.7. When we do that, we get 0.2687. For the third row or third experiment, divide 2.1 MO by 6.8. We'll do that, we get 0.3088. For the fourth experiment, divide MO4 by 7.4. We'll do that, we'll get 0.540. Keep all your values to 4 significant figures for consistency. Then for the fifth experiment, divide 4.4 MO by 7.8. We have 0.5641. Having done that, the next row we have to find cos of alpha. Alpha is the glazing angle that we use. Cos 75 degrees will give us 0.2588. Cos 65 degrees gives us 0.4226. Cos 55 degree gives us 0.5736. Cos 45 degree gives us 0.7071. Cos 35 degrees gives us 0.8192. So this is the table of value. So we're going to go to the graphing now. So we'll have our process result for the experiment. And we're asked to plot a graph of phi, which is the ratio of MO to NO against cos alpha. So we look at the values of MO over NO, that is our phi, 0.1818, 0.2687 for the 0.1818 for the 35 degree angle, 0.2687 for the 65 degree angle, 0.3088 for the 55 degree angle, 0.5405 for the 45 degree angle, and then 0.5641 for the 35 degree angle. And these angles are the glazing angles. Then cos alpha, that the cos of the angles here are obtained, 0.2588 for cos 75, 0.4227 for cos 65, 0.5736 for cos 55, 0.7071 for cos 45, and 0.8192 for cos 35. So plotting phi on the ordinate or vertical axis, and then cos alpha on the horizontal axis or the abscissor. So let's go to our graph. Based on the readings we have here, we're going to select 0.12 cm to 0.1 unit. So we'll scale our graph. here, 0, 0.1 for the first boss, 0.2, 0.3, 0.4, 0.5, and 0.6. We stop. This is our phi. Phi means MO over NO. So that we're plotting on the vertical axis. And if you look at why do we stop at 0.6? Look at the table of reading. The highest value on this is 0.564. So we now go to the horizontal axis, maintain the same scale, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and here will be 0.9. So our scale reads 2 cm, that's the boss, to 0.1 unit on both axes. So before we start plotting, we have to understand what one boss stands for. In a boss, there are 10 lines in a boss, and then each boss is 0.1 units. So divide 0.1 by 10. So each line is going to be 0.01. 0.01 multiplied by 10 will give you 0.1. So each line on both axes will be 0.01. So let's start plotting. So to plot, so we select the value to 2 decimal places. So this is 0.18. We takes 0.18, 0.258 will take 0.26. So go to this axis and locate 0.18. This is 0.1, 1, 2, 1, 3, 1, 4. Come again, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, and then this is 1, 8 on the vertical axis. So we coincide with 0.26 on the horizontal axis. We move to this place and get 0.26. This is 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, and then 2, 6. So we take a ruler. This is 2, 6. Move it up to where it coincides with 0.18. So that's going to be here at this point. So this is 0.18 coinciding with 0.26. So having done that, we go to the next value. This is 0.27 approximately to 0.42. Plot it to decimal places. 27. Now we count. This is 2, 1. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7. That should be here. Then going with 0.42. We'll move this is 0.4. So move to get it done. Let's use a ruler to trace it. So this here, it should be here. That is our 2, 6. So I'll say 2, 7, sorry. So here is a 0.4. Then 4, 2 with the second line, 4, 1, and then 4, 2, which will be here. So mark asterisk there. So having done that, the next is 0.3 and then 0.57. 0.3 is at this point already on the graph. 57, this is 5. We'll move this 0.5 line. 5, 1, 5, 2, 5, 3, 5, 4, 5, 6, and then 5, 7. That should be here. Then 0.54 on the vertical and 0.7 horizontal. So 5, 4, we look at 5, 4. This is 5, 5, 1, 5, 2, 5, 3, 5, 4 on the fourth line. I repeat, 1, 2, 3, and 4. 5, 4 coincides with 0.7. So we'll take a ruler to make it easy for us. 0.7 is, make it straight. 0.7 is at this point here. So that where it is 0.7. Then the remaining value is 0.56 and 0.82. 0.56, remember that here is 54, then 55, and then 56. So 0.56 goes with 0.82. 0.82. Here is 8, 0.8. Okay, let's make it clear. Let's get it. Okay. Here is 0.8, 0.8, 81, and 82. So that should be this position. Okay. So having done that, we're going to draw our best line. Position our ruler to get the best line. So let's see the point that give us the position that give us maximum points on a straight line. So I think is this position we're going to have here. So that is our graph. I give a maximum point on a straight line. So we'll have that. You see that 3 points are almost on a straight line, and 2 points due to experimental error are out of the straight line. So that's a good experiment. So take our slope, we'll draw a right angled triangle, taking 2 points. We're taking this last point here and the first point that fall into the straight line. So this point here, the coordinate on the y-axis is 0.56. And then the coordinate down there on the y-axis, the lower coordinate is 0.18. Then coming down on the horizontal axis, the coordinate here is 0.82. While this side, the lower coordinate for the horizontal axis is 0.26. So we'll now say that our slope, which can call S, will be change on the phi axis, the vertical axis, all over change on the cos alpha axis. So the change on the vertical axis is going to be 0.56 minus 0.18. The change on the vertical horizontal is going to be 0.82 minus 0.26. Then the coordinates. When we subtract and divide, we're going to have slope as 0.679. The slope has no unit. So because these values have no unit, they're dimensionless. So 0.679. To verify whether the experiment is correct, we can find the inverse of the slope. The inverse of the slope represents the refractive index. That becomes 1 all over 0.679. When we do that, we're going to get 1 over 1.47, approximately 1.5. And you know that for most rectangular glass block or prisms, their index lie between 1.5 to 1.6. That means we have a correct experiment here. So let's go to the precautions and the remaining questions for this particular number. So we'll go to number SIV that says 14. State 2 precautions taken to ensure accurate results. 2 precautions taken to ensure accurate results. We'll go to the solution. The precautions. 1. I ensure that I avoided error due to parallels in locating the images using the search pins. 2. I ensured that I avoided error due to parallels in reading, R-E-A-D, reading the protractor and meter rule. So these are the necessary precautions to take in this experiment. There could also be some other precautions. Go to the next question. SV says state Snell's law of refraction. State Snell's law of refraction. We'll now go to the solution. Snell's law states that the ratio or sine of angle of incidence to the sine of angle of refraction is a constant for any given pair of media. We'll now go to the remaining question. SVI says calculate the critical angle for the glass prism used in the experiment above if the refraction index is 1.5. We'll now go to the question SVI, the solution. C, we present a critical angle is given by a sine inverse of 1 over refractive index. That becomes sine inverse of 1 over, the index is 1.5, 1 over 1.5. That becomes sine inverse of 1 over 1.5 gives us 0.3667. And then sine inverse of 0.3667 is 41.8 degrees. So you are seeing how the experiment was done, very simple and accurate. So remain connected to this channel as we present to you very soon the model 2 part of this rectangular prism.